mechanism as well. See, one of our scholar is also working on this fault tolerant topologies for this switch reluctance machine. And so therefore I say this is very attractive option as a variable speed drive for an various applications, not necessarily to be like a specific to these things, and that means for a fan pumping systems, mining, machine tools, industrial automation drives, traction, battery operated vehicles, servo applications, and whatnot. Okay. So there is a wide variety of application for which this machine can be used. And here basically when I say this switch reluctance machine, the term switch reluctance, it doesn't mean that it is because the reluctance is switched. So, but it refers to the switching of the phase currents in fact, because we can have the multi-phase machine, because depending on the combination of the stator and rotor poles, so this machine classification is done with. So therefore, and depending on the specific configuration, this power electronic actuators for each phase winding will be designed with, and it comes with in fact. So therefore, the switched reluctance means here the switching of the phase currents, which is an essential aspect of the operation of the switched reluctance motor. So that is where, of course, this that is why this machine is so called a switched reluctance machine. Okay, and this switching is more precisely called a commutation. Of course, the word commutation is most commonly okay. So it is heard for in our power electronics circuits. And so the electronically commutated reluctance motor is perhaps an even more precise term than the switched reluctance motor. So that's the thing, like, and its operation basically depends on the flux linkage characteristics, and that is a one speciality, and it's also it's not a straightforward mechanism to devise this flux linkage characteristic of this machine, where this needs a special kind of a evaluation and the determination of these flux characteristics. And therefore, and here this this is like a simple constructional view of this switched reluctance machine. Here if you look at this the view, this is something like 8 by 6 combination. So here we have the 8 stator poles and the 6 rotor poles. Okay. So accordingly, so now for each stator phase winding, so we need to have one actuator for each leg, for each phase. Okay. And then if we here, what is it? This flux linkage characteristic. If we look at this flux linkage characteristic here. Okay. So this flux linkage characteristic is depending on the various rotor position. It depends. So this flux it varies depending on the position of the rotor, and determining that position of the rotor is very important. Therefore, the position sensor play a very vital role in estimating the particular position, and with respect to that the flux linkage characteristics with respect to that particular position, it can able to estimate. So that is the thing. So it means that phase current, the flux linkage, it varies with this as a function of current. Okay, and for every position, if you look at this the first, it is like aligned position. Aligned in the sense, this rotor poles is aligned exactly perfect. Okay, to this stator poles. If you look at this here, this what is that phase C poles, those are the aligned poles now in this particular view. So then other rotor poles are unaligned with respect to the stator poles. Okay. So with this, like no, for every aligned position, this okay, the flux linkage is okay. It varies in this way. But otherwise, if it is of intermediate position, so then see the flux linkage characteristic changes as a function of current, and again this unaligned position. See, this looks more or less, I think not exactly, but more or less linear curve at the unaligned position. Okay, the flux linkage behavior. But whereas for this, other than this unaligned position, see this flux linkages is not the linear function. Okay, so therefore, the control of this switched reluctance motor is not okay straightforward, and it needs a very okay see the effective controller that we need to design with. And also this rotor position need to be sensed. For that a feedback system is required, and depending on that the controller parameters need to be designed with. So anyway, and then if you look at this profile, this is inductive rotor. So depending on the rotor position, this inductive profile of this machine will also change. See this LU, this indicates what is this unsaturated inductance with respect to this unaligned position, whereas this LA is the unsaturated inductance in aligned position. So that means this is how from unaligned to aligned position the inductor profile is changing. Okay, and here you see see this rotor is aligned when diametrically opposite stator poles are excited. As I say, okay, if you look at this for this aligned poles, whenever this rotor pole is aligned, okay, and they are diametrically opposite stator poles, they are excited in a magnetic circuit. This rotating member prefers to come to the minimum reluctance position at the instant of excitation, while two other rotor poles are aligned to the two stator poles. Another set of rotor poles is out of alignment. So that means other set of rotor poles are unaligned position, but only that one set of rotor poles is aligned with the stator. Okay, so therefore then this set of stator poles is excited, whichever that okay that aligned with. So to bring the rotor poles into the alignment. Okay, so likewise the sequentially the switching the currents into the stator windings, that leads to the rotation of the rotor, that makes the rotor to rotate. Okay, so the moment of the rotor ends, that produces the torque, okay, the and power. So that involves means what is that we need to understand, this involves the operation of this switch, SRM motor, that involves the switching of currents into the stator windings. So when there is a variation of these currents into the stator windings, when there is a variation of reluctance. So therefore this variable speed motor drive is referred to as this switched reluctance motor drive. Hence this is very widely used for, like say this say applicable for the wide variable speed applications. Okay. And if you look at this comparison with the switched reluctance and the synchronous reluctance. So here the switched reluctance, in this both the stator and rotor have the salient poles. Hence this switched reluctance motor is also called as a doubly salient machine. Okay. But whereas this synchronous, in this other synchronous counterpart, the stator has a smooth bore except for slotting. Okay, but not like in the SRM. Then the other second point is the stator winding comprises a set of coils, and each of which is wound on one pole. Okay. And whereas in the synchronous, the stator has a polyphase winding with approximately sinusoidally distributed coils. Okay, in the synchronous reluctance machine. And in the so the point 3 is that excitation is a sequence of current pulses applied to each phase in turn. Whereas in the synchronous reluctance machine, the excitation is a set of polyphase balanced sinusoidal currents. Okay, but here it's not the sinusoidal currents in case of a switched reluctance machine. Okay, yeah. And the other difference is that as the rotor rotates, the phase flux linkage should have the triangle or sawtooth waveform but not vary with the current. Whereas with respect to the synchronous reluctance counterpart, the phase self-inductance should vary sinusoidally with rotor position, but not vary with the current. So means this is the difference, because see, these currents are sinusoidal in nature, but whereas here in this currents are not sinusoidal in nature in the case of a switched reluctance machine. So for that matter, now see, we have the different types of the combinations, okay, of the depending on the different combination of the stator and the rotor poles. This switched reluctance machine is classified, okay, it can be classified into the various type, like various combinations. So here see the various possible combinations or configurations is 12 by 6, and here rotor stator poles are 8, hence because the stator windings are excited in fact. Okay, so therefore say this is of like a 4-phase machine, 4-phase, okay, machine. And similarly the 4 rotor poles and 6 stator poles means it is like a 3-phase SRM. And this 8 by 10 means it is of like 5-phase, because the 10 stator poles, no. So obviously this is like a 5-phase motor. Okay, so it needs the 5-leg converter. Okay, so means depending on the number of phases, that many legs of this power electronic converters, okay, that is required. So that is how these SRM configurations can be evolved. And this okay, suppose if I say this 12 by 6, 12 by 6 means it could be like a 6-phase, because the 12 stator poles and 6 rotor poles. So therefore as it is stator poles are 12, so the number of phases is 6 phase. Okay, so like that the different configurations of this SRM can be okay, classified. And also then as I mentioned, it is a doubly salient motor, because both the stator and the rotor poles are of salient in nature, and no winding and permanent magnet on the rotor, because that is the best part and the advantage of the SRM machine. And also like as like our DC motors, DC machines, so this SRM doesn't have any brushes or commutators, all these things, because this commutation is now it is with the help of our power electronic actuators only. Okay, so that depends on our switching pattern, okay, switching technique. So therefore there is no need of commutators and brushes or any other slip rings like in a kind of a AC motors. So therefore this machine makes more special as compared to the other machine counterparts. So therefore the size and cost of a machine is also significantly less. Okay, that is where the best part of this switched reluctance machine. But only thing, see, there are some other complexities are there. See, that is where of course but here this needs a very systematic control with rotor feedback, okay, rotor position feedback. And this estimation and deciding of this rotor position angle, position angle is also a see the one main important task where we need to do this okay, rotor angle estimation. Accordingly, the switching pulse can be developed or realized. So therefore, that advantage the advantages of this motor can be listed like this. So this is like a simple and rugged construction, simple winding and insulation. Okay, simple in winding, but otherwise, and also it is more economical, as I mentioned, like because it doesn't have any brushes or commutators. Okay, all this it makes a more compact size, but with high power capability. Okay, and for high speed ranges, and also of course we can do design a, as it is a like a converter activated machine. So we can design like a fault tolerance mechanism for the safety purpose of the drive. And moreover, therefore, considering all these factors, this can provide the good efficiency and also the high torque to inertia ratio. Okay. And then it also provides the more thermal robustness. Okay. And but otherwise, when we use these power electronics converters, the switching frequency, of course, here because we know that the switching frequency is related to the some kind of a switching pattern in the PWM process. Okay, but that leads to the way, as the switching frequency increases, switching losses will increase. So therefore, it is not that advisable like in a DC to DC converters. So we no need to go for very high switching frequency also here, but otherwise, so moderately, so we can go for like a inverter grade switching frequency, like what we use like in a case of a VSI and CSI inverters for induction motor. Okay, so yeah, so like that. Otherwise, in the at the same time, suppose even if you go for a higher switching frequency, we can also just say we can devise a mechanism of like soft switching mechanism. So if possible, so that way the switching losses can also be minimized. Okay, to the extent possible, if possible. So that kind of features is also possible. Okay, and but the complexity is here. The disadvantages are the modeling of this machine is very complex, because it is because of the flux the flux linkage behavior with respect to the current, the phase currents. So they are they are non-linear in nature. So because of this non-linear flux linkage characteristic behavior of this machine, the modeling of this machine is it's not that straightforward, but it's quite complex. And it needs a lot of iterations. Even suppose if I want for every rotor position, I need to estimate this. Okay, what is that? What is flux linkage behavior with respect to the different rotor positions? And for that, even the conditioning is required. That sensing feedbacks. Okay, to sense the position of the rotor. So we need a feedback system. And here, therefore, that shaft position sensor is essential here in this case. Okay, and other thing is that the torque production has a pulsating nature, leading to a torque ripple. This is the most disadvantage factor. That is where, of course, this machine could not take much in a prominent role in the most of the at present, but otherwise there's a lot of research is going on, especially on this aspect. So like how to reduce the torque ripple, because that leads to the very high noise in the machine. So because of this, So this motor is limited to for very few applications at present, but otherwise if we just overcome this kind of, okay, if we minimize this torque ripple and hence the noise, so this motor becomes a more apt and more advisable for very see the large variety of applications, wide applications in fact, because now we are talking about the EV machine, electric vehicles. So for this electric vehicles, see, because it doesn't have any the brushes and commutators, all these things. So obviously it's a very good option rather than like a beard. So the other machine counterparts, okay, so that it makes more cost effective and most robust and okay, all these things. So therefore, and yeah, that's what, unlike AC or DC machines, it cannot run on online supply. It requires the power inverter to drive, like, because it's not like a, see, I cannot connect the direct power supply, like, okay, so the to the motor windings, but it is through a power electronic actuators, okay, power electronic switch. So hence see, obviously that makes more okay space consumption for the converter, and moreover it is like see, this converter need to be operate with the switching operation, like, okay, for that we need to design a specific pulse control mechanism. So that is another complexity. So but anyway, that we cannot forego, that we cannot, because it's the inherent behavior of this switched reluctance machine, so which is say, in which the converter is essentially, it is an essential part of the SRM drive, okay. But otherwise this the major disadvantage is the torque ripple, okay. So because these phase currents are highly pulsating in nature, okay, so because of that, because the torque is also a function of current, if the current is pulsating in nature, obviously the torque is also pulsating in nature, okay. So that is one thing. And say, because of this switching operation, even this also needs to the noise, okay, large amount of noise, because if you see the SRM, if you compare the noise behavior of the SRM machine with the other counterparts, so this produces a lot of noise, okay. It is because of so high torque ripple behavior, okay. So that, so if you can able to counter these two disadvantages, see, this machine could be a very best option for wide range of applications, okay, with high power density and okay, wide high speed range as well as high torque capability. And see, when it comes to the applications, I already mentioned, like, okay, so compressors, fans, pumps, centrifugal pumps, and also the domestic drives, okay, food processor, washing machine, vacuum cleaners, electric vehicle applications, aerospace applications, servo drives, okay, what not. So there could be several applications which we can use, but only thing is that, say, some demerit factors we need to see address for this machine. Otherwise, so this is very well suitable for various applications, okay, and it's a very good option as compared to the other machine counterparts. And what is the significance of control technology? Here the control see, the machine dynamics and its response to this applied load means that designing this control, okay, controller is a tedious process here. And anyway, see, because even see, why I am telling is that, see, right from the initial starting to the normal steady state operation of the machine, so this involves this control mechanism dynamics, okay, that's very crucial part here. So that I'll just discuss about that, what is that initial the low speed operation and the high speed operation desirability of this machine operation. And see, and then this power electron come, of course, anyway. So that's a power electron converters, it's an essential part of the machine, and wherein which this control scheme, control technique is again it's important. And protect the motor and controller itself from the damage, means where say it talks about, now we can say the protection and safety of the machine, so which can be resolved by means of some kind of a techniques, fault tolerant techniques. Okay, so by devising this appropriate fault tolerant converter topologies, inverter topologies. Okay, so that so we can make the drive is more safer and this thing. And this these are the, of course, this is a mathematical model. Simple, it looks to be very simple, but here what is that I wanted to just focus here on that. See if we can see this the flux linkage. No? The flux linkage is changing with respect to this rotor position. That is how this machine characteristics becomes more nonlinear. So if the system becomes more nonlinear, the effort of this control, okay, the control effort is, okay, it requires more effort. Okay, so that is what the say this mean, because the main this switched reluctance machine main characteristic operation, it mainly depends on the characteristic behavior of the flux linkage. Okay, so which these are very highly nonlinear in nature. So it means that see the here these are the various variables, as okay, we can rightly understand from this. Okay, so it's a simple okay KVL equation if you apply like that. See, but in this way you see the V is voltage, I is the phase current, and R is the phase resistance. Of course, any phase windings will have their own resistance. We cannot just forego those things. And phi is the flux linkage of the winding, and L is like no, it is the incremental inductance. So okay, and these are the various other parameters like speed, position in degree. Okay, so in case if we neglect the saturation, if saturation is neglected, then this flux linkage so is comes out to be like it's a function of, okay, it's a product of current and this inductance. That means even inductance is also changing. Okay, so you see this IL is also a function of the rotor position. So therefore that inductor profile is changing linearly from unaligned position to the aligned position. Okay, so that will happen. See, that's common for both, whether in the motor operation or a generator operation. So I wanted to mention like other similar all other machines, this machine can also be operated either as a motor or a generator. Okay, so that yeah, and see, as this this SRM switched reluctance machine can also operate as a motor as well as a generator, and in specific this SR generator so is becomes more prominent for some of the applications like a wind energy conversion and solar PV, even the PV okay, direct PV integration. Okay, because the required source is the DC excitation, not the AC. So therefore say that makes more suitable for the various wide standalone off-grid applications also. So therefore now here this the principle of operation, this mainly depends on this co-energy principle. Okay, so this is the mathematical model. Okay, anyway, this is well available in the okay all resources. But what I mean to say, this is say this what is it? This machine works in the principle of this co-energy. So this that's what I wanted to say. And here if you look at this torque equation, you see the function current is the square of the current. It means that even what does it mean, this I square? So even means this torque also it becomes more nonlinear, na? It's a nonlinear, say I square and dl by dt here. Okay, So therefore, this nonlinear function of current it is. Torque is also a nonlinear function of the current. It's not a linear function. And also moreover it is depending on the direction of the current as well. But however, irrespective of the, what is this? The direction of the current, because this torque is a direct function of the current in fact, but no, even though of course it is the square of the current, nonlinear function of a current, but because of this square nature, this sign depends on the slope of the inductance profile, and moreover you see the, but irrespective of the direction of this current, the torque is always positive. So that is what we can just understand from this. But otherwise the sign depends on the slope of this inductance profile also, because that means a positive torque can be generated, but here I cannot see the current can be of any direction, but it makes a positive function, right? But however this dl by dt, this inductive profile, so here this positive torque can be generated, because for to justify the motor and generator operation, so how do we need to justify? Because this torque, what could be the torque behavior of the motor and the generator like? So what can, here see this positive torque can be generated when the inductance slope is positive with respect to the rotor position, and negative torque when it is when the slope is negative. So that is how, so this describes the operation of the motor operation and the generator operation. If the slope of the inductance is positive in nature, then it is a motor operation. If it is of negative, then it's like a generating operation. So here you can just we can see clear the same principle here. Okay. So that means in the under motor operation, that inductance profile is positive slope. Okay. So based on the this equation, so it is clearly we can understand that for this positive dl by d theta, the slope of this inductance with respect to the rotor position, the change in rotor position. So that makes So under that condition, so the motoring operation can be achieved, whereas the slope is negative, then so that goes to the generating mode of operation. Okay. Yeah. So then this is about so operation of this the motoring mode and generating mode of SR machine. And when it comes to the control strategies, especially as I mentioned, so that is depending on this the back EMF developed in the machine winding in particular, because at the low speed, because the back EMF is changing with respect to the speed of the machine, right? So therefore, here these control strategies in this, the current impressed are depend on the phase voltage and rotor shaft speed and phase commutation, and these based on this current waveform, the control strategies can be classified as low speed operation and high speed operation. Low speed operation and high speed operation. Okay. What is low speed operation? Higher, okay. Okay then. So actually here these control strategies can be derived based on the your speed of operation of the machine, means under low speed and high speed operation. So what is under low speed operation? Under low speed operation, the back EMF developed is of very small, right? So therefore the current go to high values, and therefore we consider to be like a chopping mode. So we prefer this chopping mode control. So under low speed operation, okay. And what kind of chopping mode operation means? Here we can also have a hysteresis band control, or this frequency fixed frequency PWM control. So these are the two control schemes under chopping mode can be realized, can be used slow speed operation, whereas for high speed operation, as the motor picks up the higher speed under higher speed of operation, so the back EMF obviously it's increase. So therefore, so then the torque can only be controlled by varying the turn on and turn off angles of the rotor position. So, okay, so therefore under this high speed operation of the machine, so we go for the angle control mode. Okay, so this is how, say, we need to understand about this further with respect to the lower speed range and higher speed range. Okay, so to devise the appropriate controller. Okay, but this is the basic control strategy phenomena, but otherwise there could be various other advanced control mechanism we can do devise, so depending on the application also. So where in which, so we have designed this control scheme for this direct PV fed SRM drive. So where in which so we used like a variable DC based PWM scheme. Okay, like that. So depending on the some different type of applications, okay, we can also devise some okay the various control schemes as appropriate. Okay, yeah. So I think I will stop at this point. So from here onwards, of course, more on this. Okay, these are the various control schemes here, but here in the various control schemes there could be like a different say merits and demerits also we need to see. But for that matter, one thing, see, for this there is a one single pulse scheme for this high speed also. This in this control scheme, see the changeover of this pulse, okay, positive voltage to the negative voltage. It is like a sudden change in from positive to negative. So this is not a advantage factor, but this is a disadvantage rather. Okay, so but see in other two cases, if you can see, so that the changeover from this positive to the negative is not okay immediate. So but that can that leads to a kind of a some, we call it as a, like a soft switching mechanism. Okay, but this is okay. So that is how it is. So now more on this control aspect, of course now see my of course he is our academic colleague now, but he was my past research scholar in this area of work. So now I think he is already joined and he is waiting online. So in fact, as I mentioned, I have other meeting and other class also. Regular class, so I need to take a leave here. So therefore, so thank you for your patience listening. And if you have any specific clarifications, of course, anyway, so our continued my next speaker, okay, so you will clarify. Okay, yeah. So thank you all.